My name is Scott Foster. This project was development of 3D rapid prototyping of ultra-precise small parts for a Texas custom injection molding manufacturer. Working with me on this project were Brett Elay, Rhiannon Rush, and Vince Edwards. The project scope involves surveying 3D printer manufacturers and find the price and delivery for a 3D printer which can make both prototype and low volume production. This machine must be capable of 3D printing ultra-precise connectors made of engineering-grade equivalent plastics to plus or minus 10 micron tolerances, and these parts must be suitable for commercial installation to replace injection molded parts currently made on hardened tool steel dies. Here are 12 assumptions associated with this project. Note on number 11, you can take a 3D file, send it to the manufacturer, purchase parts in any material you specify, then you can take those parts, test their dimensional properties and their mechanical properties, and even put those parts in a typical field trial. Here are the cost projections from additional staffing, advertising, training, overhead, purchase the machine, installation, first-year operating expenses, and contingency reserve if necessary. These cost projections are over the first year. These are the 5-year financial projections, starting with the first year, which is negative cash flow, but years 2 through 5 have positive cash flow, using the assumptions and numbers previously provided. This project priority matrix shows the relative importance of the factors of time, performance, and cost. We've put performance as a constraint because we must hit plus or minus 10 microns. We put cost as an enhancement because the better cost means a better value, and then the time we will accept the delivery times given to us by the manufacturers. Here is a 3D printed sample from machinery maker number 2. We measured these slots that you see right here. Here's a table of the data. Our mean value was 0.1124 millimeters, so we set the upper specification limit at 0.12 and the lower specification limit at 0.10. That is plus or minus 10 microns. Here is the balance of the data. The standard deviation 0.0018, the process mean 0.1124, the CPK 1.364, and if the process were centered on the actual measured mean, the CP number would be 1.795. This process capability report for the 3D printing machine number 2 was generated using Minitab software. In this capability index published by Hessing and setting our CPK of 1.34 equal to the CP, we have a z-value of 4, indicating plus or minus 4 standard deviations inside the specification limits, 63 defects per million opportunities, and a capable process. This capability plot is provided by a 3D printer manufacturer, part size on the x-axis, CPK on the y-axis. Our part was 0.1 millimeters and our CPK around 1.34 is close to the plot provided by the manufacturer. Here are the references utilized for this report. Our group's conclusion is that the project makes sense if the market will support the sales projections and the company can achieve these sales. If the samples are 3D printed by the manufacturer in a material that functions well enough to replace an injection molded part, and that the primary stakeholders believe in the project.